Okay, let's dive into this. Welcome to the Explainer. Today we're exploring one of the most mind-bending optical illusions in modern AI 3D generation, and how an unbelievable new breakthrough is finally making it real. I mean, you've probably seen those viral AI clips, right? The ones where the camera smoothly flies through a stunning, hyper-realistic video game environment generated from just a single photograph. It looks like a physical space, but behind the scenes, that space is a complete phantom. So we're going to look at a fascinating new piece of research that takes these AI-generated phantoms and actually turns them into solid physical worlds. But to really understand this breakthrough, we first got to understand the problem. Think about it. What happens when you walk on a floor made of mist? Well, you fall right through. It's like glitching out of bounds in a broken video game. And honestly, that is exactly what happens with current AI-generated virtual rooms. Sure, they look perfectly photorealistic to your eye, but the exact moment you try to drop a video game character into that room to step on the floor or bounce a virtual ball against the wall, everything just falls straight into the void. The AI hasn't actually built a physical room. It's really just painted a very, very convincing mirage. Section 1. The aerosol mist problem and the illusion of 3D Gaussian splatting. So, to understand why current state-of-the-art tech fundamentally fails when you try to use it in an actual physics engine or a video game, let's look at what are called volumetric 3D Gaussians. I want you to playfully imagine these Gaussians as tiny, beautiful droplets of aerosol mist. When millions of these semi-transparent colored blobs overlap in 3D space, they form this stunning, photorealistic cloud. And from a distance, that cloud looks exactly like a wooden floor or a brick wall. But structurally, it is completely hollow because it's just a volume of mist. There's absolutely no hard, well-defined surface. It looks amazing for a camera fly-through, but it literally gives game characters absolutely nothing to stand on. Section 2. Flat, the 3D origami, a new breakthrough in scene generation. And that brings us to the core of today's explainer. Researchers have actually figured out how to replace that mist with something you can physically touch. They call this new system FLAT, which stands for Feedforward Latent Triangle Splatting. Now, honestly, you can just forget that complex algorithm name because it's so much better to think of FLAT as an instantaneous 3D origami machine. Instead of spraying millions of fuzzy mist droplets, FLAT takes the AI's core memory of an image, what researchers call latents, and instantly folds rigid, flat triangles to build a solid shell of the room. It all happens in what's called a single feed-forward pass, meaning it reads the image just once and bam, instantly folds out the geometry. Let's compare these two directly to really anchor this physical metaphor. On the left, you've got your volumetric 3D Gaussians, that fuzzy, unwalkable mist we talked about. It's semi-transparent, no real boundaries. But on the right, you have explicit triangle splats. This is the solid, explorable origami surface created by FLAT. Now, triangles are the fundamental building blocks of all computer graphics. By generating explicit triangles instead of that implicit mist, FLAT creates a real physical boundary. So a physics engine now knows exactly where the wall starts and stops, which means your digital character can finally walk on the floor without falling into the abyss. It's a real game changer. Section 3. Folding the math, how FLAT works without breaking. Now, what's really interesting about this is how FLAT mathematically achieves this instantaneous folding. You see, teaching an AI to fold triangles in one try is notoriously difficult. Usually the math just breaks down and the AI learns nothing at all. To solve this, the researchers designed 3 mechanical steps to decode those compressed video latents into explicit surfaces, all in a single pass. Step 1, read the 2D image. Step 2, apply a race-centered rotation. And step 3, use a product window function. Let's break down exactly why steps 2 and 3 are the absolute secret sauce that makes this whole origami machine function. So step 2 is race-centered rotation. When an AI initially tries to place flat triangles in 3D space, it frequently gets super confused by the orientation. If a triangle rotates so its edge onto the camera, well, it practically disappears. It becomes a zero area line. We call these degenerate triangles. And when this happens, the AI's learning process completely halts because it literally can't see its mistake to fix it. FLAT demystifies this by using a race-centered parameterization. Basically, this specific math anchors the triangles to the camera's visual rays, ensuring the AI places the tiles smoothly without overlapping or crumpling the paper. Then we have step 3, the product window function. Even if the AI places the triangles perfectly, they start off looking like sharp, disconnected shards of glass. For the AI to actually learn how to connect them, it needs smooth feedback, what engineers call gradient flow. That's basically the AI's ability to learn from its mistakes. This novel product window function acts almost like a microscopic blur on the very edges of the triangles during the training phase. By softening these edges, the AI's gradient flow can sort of feel the gaps between the tiles, allowing it to seamlessly learn to stitch them perfectly together. Section 4. From soup to solid, the final lightweight refinement. So, the AI does its math, it makes its initial prediction, but the output still isn't quite ready for a video game just yet. Right after the AI predicts the room, the output is what developers affectionately call a triangle soup. It's basically a collection of slightly disconnected, semi-transparent flat primitives. To fix this, Flat applies a very quick, lightweight refinement step. Over just a few optimization iterations, this process snaps those disconnected vertices right together. It forces the transparency to become completely opaque, and it sweeps away any floating junk. In literally seconds, that loose triangle soup is converted into a fully solid, impenetrable, game engine-ready mesh. No more hollow mist, just solid, explorable architecture. Section 5. Instant Game-Ready Worlds, Measuring the Results.
We know the theory makes sense, but when we look at the data, the difference is just brilliant. And this brilliantly illustrates Flat's massive lead. This chart measures geometric quality using a metric called cosine similarity that basically scores how closely the AI's generated surface angles match the actual physical reality of a room. Flat scores a massive 0.853. Meanwhile, an alternative surface method called 2D Gaussian Splatting scores a mere 0.587. Flat has a staggering lead in actually understanding physical geometric space. It isn't just tricking the eye with fuzzy blobs anymore, it is generating highly accurate physical architecture.
And here is the absolute ultimate payoff for generating real triangles. Get this. Flat operates at a lightning-fast 2400 frames per second at 720p resolution. No way, right? To put that into perspective, most high-end video games are aiming for just 60 frames per second. Because it relies on explicit triangles, the very primitive that literally all computer graphics cards were built to process, you don't need heavy, specialized AI renderers to view these scenes. It is entirely 100% ready for standard rendering pipelines. It's incredibly fast, incredibly efficient, and ready to be dropped into a standard game engine right now. So we have officially moved from painting 3D illusions with mist to instantly folding rigid, interactive worlds. The technical hurdles of gradient flow and degenerate geometry, they've been solved by Flat, entirely opening the door for instant 3D asset generation. So I leave you with this to think about. If an AI can instantly fold a solid, explorable, physical world from just a single photograph, what reality will you build tomorrow? Thanks for joining me on this explainer, and keep exploring.